Hi everyone. In day 2, this says day 3, but it's day 2 of section 5.2, we are going to use geometry to find exact areas between a function and the x-axis. So to start out with, we are going to start by graphing one period of the sine function. So we will put x and a y-axis up here. And the sine function starts at 0 at x equals 0, and it has a period of 2 pi, which means that this midpoint is pi. It has a maximum of 1 and a minimum of -1. And we are going to use numerical integration on the calculator. Numerical integration means basically very good estimates of an integral. You can treat them as exact, and we're going to do this for 1/2 of the period of the sine function, so that area right there from 0 to pi. So if you would grab your calculator, go to the home screen, and the first thing we're going to do is make sure we're in radian mode. So hit the mode button, make sure you're in radian mode. And then we're going to go back and we're going to hit math and number 9, fnint, function integration. So we're going to select number 9. And if you have a newer calculator, it looks just like an integral. So we're going to go from 0, use the up arrow, to pi, and don't estimate pi, use second and the up arrow to put pi in there. And now we have to put the function in, so the sine of x, and then we're going to jump over here and enter our dummy variable. So the integral from 0 to pi of sine of x is 2. And that's how you do numerical integration on your calculator. So this area right here is 2. So this integral is equal to 2. And we're going to use that and geometry to find the following integrals. So the integral from 0 to 2 pi, so basically we're going to integrate one period of the sine function. Now, I haven't mentioned this yet, but it turns out that if you have an area below the x-axis, it's treated as negative. So this integral turns out to be 0 because the area above the x-axis from 0 to pi is 2, and below the x-axis from pi to 2 pi is also 2, but it's treated as a negative. So that's why that integral is 0. Now we get into some transformations of the sine function, and this would apply to any function. So we're going to graph this transformation of this sine function, and that transformation would move the sine function's sinusoidal axis up 2 units. So our sine function would look like this. And again, this would be 2 pi, and this midpoint right here would be pi. And we want to find this area right here. Well, I'm going to shade in black the area that we already found and know to be 2. So this area right here is already known to be 2. But in red, we have this area added to that. Well, it turns out that that is a rectangle that has a height of 2 and a length of pi. So in this case, our integral is 2 plus 2 pi. In the next problem, we have a vertical stretch of the sine function. So I am going to graph one period of the sine function, but I'm going to try and make it look taller. So again, 0 to 2 pi, this is pi. And when we vertically stretch it, instead of going from -1 to 1, it goes from -2 to +2. And we are finding this shaded area. Well, it's kind of like any other shape. If we stretch it, it's a two-dimensional shape. If we stretch it in one direction, we're going to increase its area. And since we stretched it only in one direction by a factor of 2, we are doubling its area, and this is going to be 4. In number 4, we are taking the sine function and we are shifting it to the right 2 units. So we will take that and graph it, and instead of starting at 0, I am going to start here at 2, and the sine function looks like this. And remember, the period is still 2 pi, so this point is going to be 2 plus 2 pi, and this point is going to be 2 plus pi, or pi plus 2. So we are finding this area right here. Again, we're still minimum of -1, maximum of 1. All we did was shift that sine function over to the right 2 units. A shift or a translation has no effect on the area, so that area will be 2. Notice in number 5 we changed the dummy variable. Doesn't matter. We will graph this sine function, but here we are graphing from -pi to positive pi. So there's from 0 to pi, -1, +1, and there is from -pi to 0. Well, these two areas are exactly the same. One of them happens to be below the x-axis, so that integral is 0. In number 6, the sine of t over 2, again we changed the dummy variable, which does not matter. So I'm going to draw that over here. What kind of transformation is that? That's a horizontal stretch by a factor of 2. So we're going to graph from 0 to 2 pi, but instead of the endpoint being 2 pi, it's going to be 4 pi, the endpoint for one period, because we've stretched by a factor of 2. So this is 2 pi. Our height is still 1, minimum of -1, maximum of +1, but we did stretch this in one direction, and by stretching that in one direction, we have doubled the area, so it is now 4 instead of 2. And then lastly, what we're going to do is we are going to graph the cosine function from 0 to pi. Now the cosine function starts at its maximum of 1 at r equals 0 and goes down to 0, goes negative, goes back up to 0, goes positive. The cosine function also has a period of 2 pi, so we'll use that to help us find the midpoints here. The midpoint is pi, and the quarter point, we'll call it, is pi over 2. So our integral that we want to find is of the cosine function from 0 to pi over 2, and as you might have guessed, the cosine function, since it's just a translation of the sine function, is going to have the same corresponding areas. So this shaded area is half of the integral of the sine function from 0 to pi, or an area of 1. So as I mentioned, we focused on the sine and cosine functions because they're relatively straightforward, especially to do transformations with. But you can treat any function this way, and you can find integrals by using areas. We're going to take a look at the inverse sine and the inverse cosine function here, and I wouldn't expect you to know how to do this one directly by area, but I would expect you to know the relationship between the graph of the sine function and the inverse sine function. So we're going to start out by graphing the sine function. And the sine function, as we just got done talking about, here it goes from 0 to pi. That's going to be more than enough for us. And this point right here is pi over 2. And we know that this shaded area from 0 to pi over 2 is going to be 1. All right, now how does that relate to the inverse sine function? Well, if you recall from pre-calculus, if you reflect a function over the line y is equal to x, you switch the x and the y, and you get the inverse function. So the inverse sine of x, instead of going from 0 to pi over 2 on the x-axis, is going to go from 0 to pi over 2 on the y-axis, and instead of going from 0 to 1 on the y-axis, it's going to go from 0 to 1 on the x-axis. Now, you're going to have to fool around with this or think carefully about it, but what the graph actually looks like when you reflect it over the line y is equal to x is like that. And so what we want to find is this shaded area right here, and we can use the following to help us. We know that if we were to fill this out here, we have formed a rectangle with a width of 1 and a height of pi over 2. So the area of the rectangle, shaded area, non-shaded area combined, is going to be 1 times pi over 2, or pi over 2. However, we want to find the shaded area in black there. Well, it turns out we already know the shaded area in red. It is 1 because we just found that area a moment ago. So the area that we want, this integral, the integral from 0 to pi over, from 0 to 1 of the inverse sine of x is going to be equal to the area of the rectangle, which is 1 times pi over 2, or pi over 2, minus the area of the red shaded region, which we happen to know is 1. So pi over 2 minus 1. What I'd like for you to do now is I'd like for you to pause the video and try that approach with this function, the inverse cosine function. When you're done, unpause the video and take a look at your solution and compare it to mine. Turns out that in this case, the integral from 0 to pi of the cosine, 0 to pi over 2 of the cosine function is actually the same area as the integral from 0 to 1 of the inverse cosine function, which is 1. The next thing we want to do is we want to do a couple of examples with geometry strictly, like areas of rectangles and triangles and circles. So let's do this problem. First one, the integral from -2 to 2 of the opposite of the absolute value of t plus 7 dt. So again, our dummy variable t does not matter here. So the first thing we want to do is figure out what this graph looks like. With the negative in front of the absolute value of t, it takes the absolute value function and flips it over the x-axis. So instead of looking like a V, it looks like an upside down V with a vertex at the origin. And the plus 7 moves it up 7 units. So the graph basically looks like this. There is a vertex here at 0, 7, and it slopes downward like that. And we want to integrate from -2 to +2. So what we need to do is we need to plug -2 and +2 in and figure out what the coordinates of these 2 points at the left and the right are. So if you plug +2 in, you get 5. And if you plug -2 in, you get 5 as well. So this integral that we want to find is represented by this total area here. And we're going to break it into 2 parts. One is a triangle, and the other is a rectangle. And so we're going to use geometry to find those 2 areas. The area of the triangle, 1/2 times the base, which is 4 units, times the height, which is 2 units, plus the area of the rectangle, which is 4 units, length times height, 5. So we have a total area of, what do we have? We have 20 plus 4, or 24. And that's how you find areas using geometry, or integrals using geometry. We're going to do one more example here, and this one is the integral from 0 to 5 of the function the square root of 25 minus u squared du. And you might be looking at this function, the square root of 25 minus u squared du, and not recognizing it. So what I'm going to do is I'm going to change the variable to x. So 25 minus x squared. And I'm going to set that equal to y, replacing function notation with y. And I'm going to square both sides. So y squared is equal to 25 minus x squared. And then I'm going to put both variables on the same side. So x squared plus y squared is equal to 25. And hopefully you recognize that as a circle centered at the origin with a radius of 5. Now, the part that we are interested in is the positive root of 25 minus x squared. So those y values all have to be greater than or equal to 0. So essentially, we're only looking at the top half of that circle. So here's the top half of the circle. It's centered at the origin, has a radius of 5, so this point is negative 5, 0, and this point is 5, 0. And we are integrating this function from 0 to 5. So 0, 0, and that means we are finding this area. So our integral is going to be, make some room here, equal to 1/4 times pi times 5 squared, or 25 over 4 pi. And that's how you use geometry to find areas between functions and the x-axis.